Good afternoon, everyone. I think we will make a start. So welcome to the Center for Energy Systems Integration and Durham Energy Institute webinar. This is on to present information around a case study on an integrated zero carbon hub. So today, my name is Tony Roskilly. I'm PI for this case study, and I'm an associate director of CESI and a director of Durham Energy Institute. On the panel as well, we're joined by Professor Simone Abram, who is a co-investigator on CESI and also a director of Durham Energy Institute. And the main speaker today is Dr. Yiji Lu. He's the co-investigator on the case study and a fellow of Durham Energy Institute. Also, our other colleague that is a member of the team with this case study is Professor David Flynn, who's professor of Smart Systems at Heriot-Watt University. Next slide, please, E.G. Next one, please. So across the UK, I'm just going to set the scene. So across the UK, 80% of the heating in buildings and in industry is generated currently through utilization of natural gas. The transitioning to use of electricity, hydrogen, and bioenergy have the potential to make a significant contribution towards delivering low carbon heating. With respect to hydrogen, one of the potential approaches is to use the existing natural gas distribution network to transport hydrogen. As might be expected, the immediate challenges related to this is the safety and the cost to retrofit. There are a number of demonstration projects exploring these aspects. For example, the new £11 million Future Grid project, which will build a demonstration facility to replicate the national gas transmission system and will be linked to the existing H21 High Street project, which is exploring the safety of using hydrogen in the gas network and in homes, and utilising hydrogen-ready appliances. However, hydrogen deployment provides more than an opportunity to decarbonise heat. It offers the mutual benefits to decarbonisation of transport, the wider electricity energy system provides the opportunity for energy storage solutions and other energy services. Next slide, please. So there is the potential on a national and international scale for the existing gas grid infrastructure to be modified and used to deliver natural gas and hydrogen mixtures, or even up to 100% hydrogen produced from clean sources. For example, using steam methane reforming with integrated carbon capture and storage to produce blue hydrogen, or through electrolysis from abundant renewables to produce green hydrogen, and for this to be distributed across the UK. There are a number of projects which have been funded by BEIS to demonstrate hydrogen production at scale. That's the key for it to be an economically viable option. So HyNet, Hyper, and Acorn are blue hydrogen projects producing hydrogen from natural gas reforming with the integration of carbon capture and storage. Gigastack is a green hydrogen project to demonstrate the synergies between offshore wind and electrolyzers at a gigawatt scale. Dolphin is another project, which is a green hydrogen demonstrator for, I think it's a 2 megawatt demonstrator, and exploring hydrogen production from deep water floating offshore wind and integrated water electrolyzers. There is a European hydrogen backbone vision to repurpose existing gas infrastructure and to produce new dedicated pipelines and compressor stations across the whole of Europe. So you'll see that in the figure on the left. This leading to the interconnected hydrogen transport infrastructure. And you'll see that there is a link dotted link across to the UK. There are plans to produce hydrogen in global locations where there is abundant access to renewable energy. For example, Tunisia, through the use of solar PV, producing green hydrogen, which can feed directly into the European hydrogen pipe network. Also, more globally, there's a lot of activity between Australia and Japan. They're collaborating to produce and deliver hydrogen from the renewables in Australia, and for that to be shipped in liquid hydrogen tankers to Japan. Next slide, please. So how best to use hydrogen at a local scale? So we've got this national, international transmission of hydrogen. So local, at a local scale. At present, the most of the focus has been on to distribute hydrogen through the gas network to individual homes and businesses. An alternative is to distribute hydrogen to zero carbon energy hubs, which would integrate intelligent thermal networks with hydrogen fuel cell or hydrogen fueled, I would say, combined heat and power to provide a number of energy services. So these hubs can provide electricity, they can provide heating and cooling services across urban areas in localized industrial or residential networks. This will avoid the need for hydrogen combustion in boilers in individual properties and businesses, and also incorporate electrical and thermal storage to maximize the efficiency and the operational flexibility of the system. The hub could also provide the opportunity to integrate transport energy services, providing hydrogen fuel refueling and electric vehicle recharging, since these energy vectors will also be available within that hub setup. So the solutions proposed represent the kind of hydrogen-enabled future energy system, integrated energy system envisaged by the net zero pathways presented by the Committee on Climate Change. So that's just an outline of the concept or the focus of this this case study from CESI. Now, my colleague, Dr. Yiji Lu is going to do his presentation on the building blocks that we're putting together to carry forward this research project. Over to you, Yiji.
Hello, good afternoon, everyone, and thank you for attending this webinar jointly organized by the CESI, the National Center for Energy System Integration, and DEI, the Durham Energy Institute. My name is Yiji Lu, and today's talk will provide an introduction on the integrated zero carbon hub concept, currently developing at Durham University. The first one, I would like to provide an overview for this zero carbon hub and the currently hydrogen economy introduction. To give an overview of my talk, include a short description on the research background and provide the insights on the state of the art for this research technology development on hydrogen energy systems, including hydrogen production, storage, transportation, distribution, and utilization. We are currently facing a dramatically energy system transition from carbon-based economy to net zero economy, potentially to achieve the net zero target in 2050 in the UK. There are three colored lines illustrated in this diagram. The red line illustrates the carbon economy using the fossil fuel-based energy to provide for the transport and industrial application. The blue line illustrated the utilization of renewable energy linked to the electricity network to produce electricity. Both red and blue line is the existing carbon economy. The added value using hydrogen network is the hydrogen can be produced from both natural gas and the renewable, linking showing as the green line illustrated in this table. So the hydrogen production can be mainly classified as three types. I have included the pink as well. So the three types is called gray hydrogen, produced from natural gas without using carbon capture. And if the carbon capture storage technology is linked to is used for the hydrogen production from the natural gas or biomass or coal through the reforming chemical gasification through a process, it's called the blue hydrogen, which can potentially remove CO2 from the chemical process. The hydrogen can also be produced from the renewables, such as wind power, solar energy, geothermal process through the electrolyze process, mainly electrolyze process, which is called green hydrogen. Another one is called pink hydrogen, produced from using the nuclear power. The data I would like to bring forward is this: currently 96% of hydrogen is currently made from the reforming of fossil fuel, 48% is made from natural gas, 29% is made from the liquid hydrocarbons, and it says around 80% of hydrogen is made from the coal. Another currently emerging technology people are exploring is using green hydrogen through the electrolyze using of the water using renewables. It's about 4% of currently on the market. It's 4% of hydrogen is made from water electrolyze. As long as the hydrogen has been produced, the hydrogen has to be stored first, and there's a lot of challenges currently facing to store the hydrogen. The hydrogen can be stored either in physical storage tank or in a sorption storage process. The hydrogen is not as illustrated on this figure, considering different fuels to store fuels. Ideally, what we are looking for as a fuel, we would like the fuel to be located at the top right corner, which can reach the maximal, ideally, volumetric density and energy density compared to other potential fuels. The hydrogen is, compared to other fuels, the hydrogen is unfortunately cannot reach that high volumetric density compared to other potential fuels, but compared to the natural gas, the existing infrastructure using for the heat network, the hydrogen has around 2 to 3 times of the gravimetric energy density compared to natural gas. The hydrogen, the point I would like to emphasize here is hydrogen has to be stored in a compressed way, either currently set by the industry is either 700 bar or 350 bar based on the design of the different infrastructure application in order to provide an overall high energy density as a fuel, clean fuel in the energy system. The hydrogen can be transported mainly through 3 different ways: by road, through pipelines, and through ocean, such as the currently developed by the Australia and Japan way. The key focus of this project is we would like to develop technology on the back after the delivery sites to deliver innovative solutions using hydrogen to achieve a clean, affordable energy system. The hydrogen can be used either for heating directly using a hydrogen boiler, or the hydrogen can be used for electricity production through either a fuel cell or hydrogen engine, hydrogen turbine. Hydrogen can also be used as a gas-driven heat pumps to provide upgraded thermal. The key objectives of this one is to investigate hydrogen engine and hydrogen fuel cell technologies to develop a combined heating and a power energy system using these 2 objectives. First, we have compared different fuel cell technology and collected from the literature, compared 5 different types of fuel cells to consider the operational temperature, operational range of these different 5 fuel cells. The PEM fuel cell and the solid oxide fuel cell has been identified as the 2 key components that we would like to use and develop in the submodels, because these 2 fuel cells technologies can be recognized as representative fuel cell. In PEM fuel cell can be recognized as a low temperature fuel cell, and the solid oxide fuel cell can be recognized as a very high temperature fuel cell. As we can see, the operational temperature is extremely high compared to other fuel cell technology. These 2 representative fuel cells will help us to understand the effects of using either both low temperature fuel cell and high temperature fuel cell, understand the effects of these 2 different fuel cells in a heat networks for combined heating and power application. Another point I would like to emphasize is PEM fuel cell is most commonly used as a small scale application, and solid oxide fuel cell is used as a large scale application. So by selecting these 2 fuel cell technology, we can cover both the temperature range from low temperature to high temperature, and the application range from small scale to large scale application. The figure presented on the left side is a simulation process to understand the amps, volume, power of a fuel cell, and this figure is just to illustrate how the simulation process can be conducted and whether how to potentially accurately simulate a performance of fuel cell technology, and this can demonstrate that the simulation process to simulate fuel cell can be potentially conducted accurately through the simulation process. This figure, I would like to emphasize to include these figures to illustrate that the fuel cell technology, it has a theoretical maximum power, which is not actually currently used in industry and in application, because in the theoretical range of theoretical maximum power, the overall efficiency of the fuel cell is not in the optimal design condition, and the chemical reaction for this in the range of theoretical maximum power is not stably controlled. And this is the reason that we have to develop accurate simulation to simulate just the in the range of the simulation in the range of the optimal fuel cell performance, in order to making sure that the system designed in this in the hub is within the highest overall performance system. This is a energy flow of typical fuel cell technology. As we can see from the very beginning, the hydrogen, 100% of energy is from the hydrogen. Then the hydrogen can be converted through electricity using a fuel cell technology. In a fuel cell, in this diagram, 50% of hydrogen fuel has been converted into electricity, and there's 45% of heat. 45% of fuel energy is actually dumped to the environment as a thermal energy. There's 5% of hydrogen is pumped back to the unit. So this 45% of heat generated from the hydrogen-based energy system, if we can effectively, highly efficiently recover this thermal energy as a combined heat and the power, theoretically, the maximum overall efficiency can be reached as high as 95% of overall efficiency. And however, there's not all of the thermal energy dumped from the fuel cell can be recovered. There are some very low temperature generated from a fuel cell, which is difficult to be recovered. This is a diagram of a potential of a fuel cell energy system, how to recover the thermal energy from a fuel cell technology. Starting from the heat generated from the fuel cell, the thermal energy can be removed from either through the heat pipe technologies or through air cooling process, liquid cooling process using either water or coolant energy. Alternatively, it can be removed from the fuel cell through the phase change cooling process, then stored in a thermal energy storage unit as a to drive a heat recovery technology. Then the stored thermal energy can be used directly for heating, either to heat up hot water or for space heating application. The thermal energy stored in the thermal energy storage technology can also be used to drive a sorption chiller using thermal-driven absorption chiller or adsorption chiller to produce both either air conditioning or water chilling function to provide a cooling effect. Alternatively, the heat can be converted directly to electricity through either a technology called organic Rankine cycle or through the thermoelectrical generator to convert dumped thermal energy from the fuel cell technology directed to electricity productions. Some of the thermal can also be recovered for self-servicing for the fuel cell application, which will be used to improve the overall energy efficiency for a fuel cell unit. This figure I would like to present is to illustrate an experimental data-based results. This is a 3 kilowatt fuel cell unit, which the design rated power of this fuel cell is 3 kilowatt to produce electricity using hydrogen as the fuel. At the design point, if the thermal heat recovery process has been used, the thermal efficiency of the heat recovery system is around in the range of 40% to 45%. If the thermal energy can be effectively recovered based on the experiment data published by the author, the overall energy efficiency on the design point can be as high as 80%. we can see it's a dramatically improve of the overall energy efficiency if the fuel cell combined heat power system can be potentially used. And the result has demonstrated that this 3 kilowatt fuel cell, it's possible to generate sufficient daily hot water demand for a typical family, and the electricity is sufficient to provide the electricity consumption for a typical family application. This is a diagram to illustrate the concept of this integrated zero carbon hub concept, and some simulation models that submodels that we are developing. Starting from the input, so the hydrogen hub is using renewable electricity to use the electrolyzer to produce hydrogen from this side. Then the hydrogen can also be delivered from a trunk or pipeline. Then the hydrogen will be stored in a hydrogen storage in the form of hydrogen storage. It can be a tank or it can be other hydrogen storage technologies. The hydrogen stored within the hub is utilized through the fuel cell to provide green electricity. Then the heat removed from this fuel cell, it can be a solid oxide or a pump fuel cell, is stored through the thermal storage process. The stored thermal can be then utilized to provide heat for heat networking. Alternatively, the thermal energy stored in the thermal energy storage unit can be used to drive a sorption chiller to provide the cooling, to provide for the cooling network. The electricity generated from the fuel cell technology can also be used to charge a vehicle, a hydrogen vehicle or bus or a bike. And we need a battery technology linked to the fuel cell technology to balance the output and input from the fuel cell system. The electricity can be used to supply to the grid directly to provide green electricity through this process. Therefore, this hub concept can provide 5 different energy services, including electricity and cooling and the hydrogen refueling process through the hydrogen storage tank, then upgrade the pressure through the compressors, and can be potentially used to charge the vehicles, and the battery charging service. And this is a short description of this concept in this integrate the zero carbon hub concept. And thank you very much. This is my presentation.
Thank you very much, Yiji. That's great. We've got a couple of questions already, and then I would encourage people to add your questions into the chat on the right hand. Well, depends on your screen, but on the chat on the side of the window, that would be great. Can we start with a question from Richard Lowes, who's asking about the suitability of the gas distribution network around energy capacity, and he's also asking whether there are reductions in the potential use of line pack, for example, as a flexible storage mechanism.
Yes, Tony. So maybe I can try and answer that. So I think, obviously a lot of the projects that are being conducted at the moment, the demonstrations and the development programs are aware of this issue. Obviously, the amount of energy that you can effectively store within the line pack and how much that you can actually deliver is significantly different with hydrogen. So it has an impact. I think it's pretty clear that additional hydrogen storage needs to be incorporated, not just within the line pack itself. There's a lot of studies that are being conducted at the moment that are exploring hydrogen storage at scale in geological ways. So I think that has to be taken into account and in part of this study. So in terms of these hub concept, we're actually looking at integrating local storage. Obviously, not again, it depends how widely these hubs could be distributed, and therefore aggregating up to potentially a significant amount of storage. I hope that answers it partially.
Thanks. And I know there's been a lot of questions recently about whether the gas distribution and transmission system are suitable for carrying hydrogen and so on. And we'll just say that the recent research that we've heard about through National Grid has shown that they are pretty confident now that the newer infrastructure is quite capable of handling hydrogen. Yeah,
I think it's fair to say that the gas distribution networks and their studies have not thrown up any major technical issue to prevent the network from utilising of hydrogen.
Which actually leads us into a question from Dave Jenkins from Harriet Watt, who asks about, given that heat pumps may well become an established market for residential heat, what's the argument for dedicating hydrogen for residential heat networks when there's likely to be competition and demand for hydrogen in other areas where it might be more appropriate, especially in transport and in industry, for example? Yeah, I mean, you could argue equally that electricity as a high-grade form of energy is equally up for competition for what that's utilised for. I don't think that say in 20 years' time, I don't think anybody could say that heat pumps are the solution. They're currently not really the solution for the UK at the moment, but mainly economically. But you could argue for the UK climate. We have an unfortunate situation where we have a cold but also humid winter. So there are arguments against heat pumps in that sense. So all technologies will develop, and whichever will win out. And I think it's clear that there is a major push and a major investment from governments across the world, not just in Europe, that hydrogen will play a big part. All of the modelling that's gone into BEIS, informing them of all of the energy mix scenarios out to 2050, have hydrogen as a major energy vector. Whichever one that is, we don't know. Equally, this hub concept it could be utilized as an energy center within centers within an industrial context, in an industrial cluster. What we're doing in this project is exploring all eventualities or all possibilities of where that where hydrogen can play a role in providing more than one energy service. And I think that's important because you maximize the efficiency, up to at least 90% utilization of that hydrogen, and use that in an integrated and effective way. Thank you. Yiji, do you want to add anything to that?
I think I agree on Tony's opinion. Yes, heat pump will be a potential solution, and I see quite a lot of industry and academics currently developing heat pump technologies, and I see heat pumps as a potential solution to provide heating solutions in the UK and in the Europe. And I think in the future energy system, it won't just be alone for a hydrogen economy. It will be a combination of different technologies, including heat pumps, including hydrogen economy. We are developing this technology, not saying that hydrogen zero carbon hub will replace everything. It's not an ultimate answer to the future energy system. The future energy system will be a totally integrated of different type of solutions. I still believe the fossil fuel will play a tiny little bit of my personal. I still believe fossil fuel will still play a tiny bit of roles in the future energy system. For example, if we are going to use a truck in a very rural area, which hydrogen cannot be supplied, we can potentially develop carbon capture technology linked to agriculture application trunk. It's my personal view, and I think this will be a combination of all of the potential technology to provide both heating, cooling, and power generation in the next couple of 50 years in the technology development. And I agree that a heat pump is a promising technology, but heat pump may not be the ultra solution. I think it will be a integrated different various energy technology for providing heating solutions in the future. Yes, sorry.
Thanks. Yes, I think there's a consensus emerging pretty widely now that it's horses for courses, isn't it? That we're not going to see one solution that fits everybody, but we're going to have to bring in a whole diversity of options. And I think from my perspective, one of the big problems in the promotion of heat pump is the focus on domestic heat pumps, one per dwelling. I think there are much better uses for heat pumps that we could maybe discuss on another occasion. So there's a couple of more questions, I think, which develop this. I'm going to not take the next one in line, but the one that's most relevant just to this discussion that we're having now, which is a question from Tom Noland asking, what would be the advantage for householders? Again, we're back on a focus on householders, but what would householders benefit from using a hydrogen hub? Are you seeing it, what's the role for the hub specifically in domestic heating, or is it more important that it provides an optional flexibility through the other things it can supply?
So I guess the economics hopefully potentially would stack up to make the case for it to be viable in terms of the heating for individual houses or individual buildings or whatever. That is the link, and maybe that wasn't made clear enough in a district heating network or a district cooling network. So they're actually the adoption of thermal networks and cooling networks has been adopted more widely and strongly promoted from a UK perspective, primarily on the basis of being able to provide heat at a more affordable price. So what the hub will provide is the heating via a heat network. On the kind of byproduct of that, or the co-products of that, are the other energy services. So that's electricity that can go into either the national or a local grid, and the charging facilities, the cooling. Cooling is actually often ignored. Cooling demand across the UK and the rest of the world in particular is increasing, while heating requirements are reducing. So cooling is going to play a much greater role, and if you can provide both within both heating and cooling within that, with an integrated system, that's an advantage. So I guess it's the economies of scale. What we're saying is one option, which is being heavily promoted, is that every individual house has a hydrogen gas boiler, and going down that route. So everybody in individual. So the benefits of a heat network as opposed to that route are well known and well promoted. I guess the other thing that isn't necessarily known so much or thought about so much is Nox emissions and the other environmental impact of individual boilers and individual combustion of even if we move now down towards hydrogen, you still have to deal with the NOx issue, and that's a much more potent greenhouse gas than CO2, and also has other health issues. So in terms of an urban environment, a city like London, that is number 2 on the list of gas boilers are the number 2 on the list of production of NOx and those associated problems with it.
Thanks. I mean, one of the things that ties these questions together, some of these around, you know, the commercial viability and so forth, is around scale. So we talked sort of in an abstract way about a hydrogen hub, but we maybe could ask questions around, could they be produced at different scales? So for example, could you have a hydrogen hub on a hospital site where it provides both heating and cooling and power and maybe fuel cells for hospital transport, or does it need to be at the scale of a city, or should it be just one company? Could you say a little bit about how you envisage these working out in practice?
So again, that's part of the study. It won't be part of this CESI project study. It'll be part of a new EPSRC funded project, which is going to be looked. That's a 3-year program, a much larger piece of work, and that's going to look at it from a national scale and national scale modelling at what kind of granularity would be the sensible way forward, looking at the kind of I guess socioeconomics of it and the techno-economics of it. But again, you could see that at different scales, like you said, you can within an industrial complex or even a hospital, like you mentioned. There are lots of all of these kind of energy services are required at the moment. They're individually supplied but not in an integrated energy system way where you can get efficiencies, and also not integrating any form of thermal storage or electrical storage to again improve on the overall efficiency and the flexibility of the system. So I guess I think it's not fully known where it's best to kind of initially deploy. I guess, you know, following on the question about the heat pumps, then we believe that hydrogen is probably going to make the biggest impact within the industrial clusters first, because they're the primary source of hydrogen production at the moment. You know, there's this competition for the hydrogen town. I would imagine that that will be the winner, or the first demonstration of that. It would make sense for that to be very close to where the source of the hydrogen is. A lot of interest in offshore wind, electrolysis, hydrogen production. Again, our kind of northeast coast, very large wind, offshore wind setup. Again, look. A good opportunity to feed into the industrial clusters, and so, you know, I think probably as a possible first kind of application would be in industrial sector, where you still require thermal networks and a lot of interest in using thermal networks, heating and cooling networks.
So we've got a couple of questions around sort of links between hydrogen hubs and other kinds of energy vehicles or vectors at the moment. So, for example, could you see the hydrogen hub being accessible to, you know, could you incorporate biogas from different sources, or how would it link into other kinds, you know, could you have an electricity hub as well, or, you know, would it be linking into other vectors, or is it kind of, this is a focus on hydrogen?
Well, this project was primarily focused on hydrogen and the challenges of utilizing 100% hydrogen. There's a much possible wider scope to include other forms of and other energy vectors. It could be within the same system. I mean, you could integrate a boiler system, a biogas boiler system with a fuel cell. You could even integrate, if we're using a low temperature fuel cell, you could also integrate the use of, to do thermal upgrading using a heat pump. So there's kind of a lot of opportunities to look at other vectors and other technologies. This is kind of this first step is to look at it a little bit more selectively, so that we can make some progress, but then we could add any other scenario to it.
There's a question about hydrogen for maritime transport. I think that might be a bit of a distraction to the current
I can answer that.
But if you want to give a quick answer, that would be thanks.
Yeah, no, I can answer that. So I think that hydrogen will play a major impact in maritime transportation. I think that will be both in ports, but also in shipping itself. What form that will take in the long run, as you know, that the maritime sector has been shifting towards adopting LNG as a fuel of the future. That's being overtaken by events by IMO now mandating around carbon emissions, which weren't there before, and that will come in very, very strongly. So when I say hydrogen will play a role, that will be in hydrogen in itself, or hydrogen carriers. So ammonia and the creation of ammonia from green hydrogen and utilizing that as the form of the energy store and the fuel for marine is another strong bet.
Okay, I'm going to add a question here, but we've still got 10 minutes, so if people want to either follow up their questions or ask additional questions, please do drop a note in the chat. That would be great. I've got a question about timescales. So you mentioned, Tony, that we've got a project starting soon, a 3-year project looking at these hubs in more detail. So that's 3 years of research. How far away do you think we are from moving forward on getting hydrogen hubs up and running, or getting hydrogen into the UK economy at least?
So all of the technology exists. All of the technology exists at the moment. And so it could be implemented now. I guess the way that you would, the reason for the research is to look at ways to utilize all of that technology, all of those in a more efficient and effective way, and to explore all of the other aspects of it, the public acceptance, the social aspects of it, as well as the technical. So from a technical perspective, we're building a demonstrator of the hub now at a smaller scale. So to demonstrate that, but there's new technology that's coming along all the time. One of the things within Yiji's presentation is one of the issues is storage, and whether you store that in compressed form, or you store it in a MOF, or some physical or chemical sorption process or whatever. There's still a lot of things to do there, but we're building a demonstrator. It can be done now. We would like to move towards building a bigger demonstrator operating in real life. It would be fantastic for that to be in the Teesside industrial cluster, for example.
Thanks. And people talk a lot about public acceptance, but I think probably more critical is both government and industry acceptance at the moment. We've seen obviously a lot of funding now going into hydrogen research, and National Grid and the gas networks and so forth are very much involved in that. Do you see is there any major resistance to this? Who's blocking this potentially, or is it just a case we just need to get on with it?
Well, I'd say, for example, if if we pulled together this project, I don't know, even 5 years ago, you probably wouldn't include the transport part with hydrogen, but that's changed. That's you know, there's a big impetus from government on and seeing the role for hydrogen in transport, and that particularly around freight, but even coming down, you know, into the kind of a crossover twilight zone, I guess, between where battery electric vehicles just about kind of make it and where hydrogen could play a role. And you know, that kind of that twilight zone, that area is kind of being blurred and becoming increasingly blurred. The more hydrogen, if hydrogen can be, you know, predictions that it could be equivalent price to natural gas, then you know that is a game changer in terms of the economics. But I guess where a lot of the real reaction against hydrogen is around efficiency, and why would you use and particularly green hydrogen? Why would you use you know, high-grade electricity form of energy to go down that route? But you know, at the end of the day, you know, I spent a lot of time trying to commercialize grid-scale energy storage, and it's pretty soon that you realize that efficiency isn't the dominant factor in any take-up of any technology. It's all down to money. In a sense, it's all down to the economics of it and whether it stacks up in the longer term. And you know, if the investment in the technologies, the hydrogen technologies that we've been talking about, has happened in the same way that we've done with battery technology, the same way we've done with wind technology, then you know, we could easily get to a position where those barriers disappear.
So is there like one or two identifiable things or actions that could be taken now by particular actors that you think would make all the difference, or are we just going full steam ahead now? What's the next steps?
Well, I think I mentioned in my introduction that there's a number of many millions of pounds that have been invested by the government in demonstration, and these are demonstration projects to produce hydrogen at scale. And you know, that once those are taken through, that actually will potentially prove the business case for hydrogen, and prove the economic stack up for hydrogen, and what that scale would be. Again, you know, if you link that to what's happened in the development of offshore wind, we would never have thought that we would get to the scale of deployment of offshore wind that we've got in such a short time frame. And you know, that's been stimulated by government activity that has given the confidence to the industry and to the market to be able to take that forward. And I just think that we're in that position now. There's this hydrogen town competition and demonstration. There's a lot of enormous amount of interest in hydrogen bus demonstration across the world at the moment, and equally within the UK, Liverpool and elsewhere. So I guess with this demonstration of the technology and this confidence, and that kind of builds up, I think then it'll be an opportunity for those that are working in hydrogen research to bring forward some of the technologies that will change it even further. Yeah, I mean, a lot of technologies were kind of very low performance, very low efficiency at the very beginning, but you know, we changed from diesel engines to having about a 5% efficiency to up to 50% efficiency over a period of time. You know, we can always improve through research.
Absolutely. And, you know, one of the things that I think is really important going forward is that we show, you know, that the benefits need to be shown first, because when it comes to things like locating, you know, this hub's got to be in a place, hasn't it? It's got to be somewhere, and it's got to go through the planning system, and people have got to be happy to accept that it's going to be appropriate. So we need to show what the benefits are, I think, quite early on, and have the first ones in places where they're not controversial, because what can kill an industry is to come out with a brilliant technology, shove it down somewhere where people don't want it, and then you immediately generate a huge hostility. So it's really important to think about the kind of the next steps, who needs to be involved in, you know, even the aesthetics of the infrastructure might maybe need to be considered quite early on so that it's more appealing and so forth. I think these things can really make a difference and perhaps need to come in pretty early. So actually in our next project, we're going to have to think about that very carefully as well, aren't we?
Yes, yeah, definitely.
Are there any additional questions? There was another question about biomass, but I think perhaps we've covered that. Or Yiji, would you like to add anything that we haven't covered already?
Yeah, we have asked one question from Tom Noland. He or she asked whether they receive the energy as a gas or as electricity. So the concept that currently we are developing is using hydrogen as a more or less like an energy storage process. So the energy delivered to the household application, it will be a gas. We are exploring the potential of hydrogen delivered to the household using the potentially a gas network to deliver through the existing pipelines to deliver hydrogen. So the the position of the UK currently in the industrial perspective, currently we are exploring 20% of hydrogen as the added up to the existing natural gas to do a feasibility study from one of the project. Then the next step for this project is to explore the potential of using hydrogen as a 100% of pure fuel to provide heating in a heat network. So the concept of this hydrogen hub, as we would more or less like a refueling charging station to store all the to store the hydrogen, then deliver different energy service to the household, to other applications, things like heating, cooling, electricity charging, and the battery energy storage things through this hub. Yes, the energy received in a like the question, the energy received in a household that we mainly will be received as a gas, hydrogen gas supplied to the household application. The electricity can be recognized as more or less like we have plenty of the hydrogen where we have no place to store. Then we convert the hydrogen into electricity supplied to the grid, or convert the hydrogen into electricity for some specific application. For example, buses charging and the electricity for household application. It's something that I would like to add up. Thank you.
Thank you. That's great. I think we're going to have to close because it's coming up for 2 o'clock. Thanks very much, Tony. Thanks very much, Yiji. Thanks everybody for joining us and for bringing your questions. And I'd say watch this space. There's a lot more to come.